Hello everyone and welcome back to Techmine Guru. I'm your coach Supratim. If you have ever felt overwhelmed by complex data structure, you are in the right place. Today we are tackling Mastering Trees Part 2, BST, which is known as Binary Search Tree, which will be your ultimate guide to binary search trees. Here is our path to mastery for today's session. We are going to start from the foundational golden rule of BST. From there, we will look into searching and inserting data in a BST and then finding minimum and maximum values in a BST. After that, we will face a boss level deletion problem where we will master 3 different cases. And finally, I will share you some pro tips on building and validating this binary search trees. So let's dive right in. So what exactly is a BST? At its core, it is a data structure that organizes data hierarchically. So the magic lies in its design. For every single node, all the values in its left subtree are smaller and all the values in its right subtree are larger. This property makes search operations highly efficient. But why should we use BST in our program? First, they offer efficient search, which is significantly faster than linear search for large data sets. Second, they give us the ordered data. That is, an in-order traversal yields elements in sorted order, useful for range queries and sorting. Third, they have a dynamic structure that easily accommodates data growth through insertion and deletion. And finally, they are flexible and versatile, serving as the foundation for advanced structures like AVL trees, red-black trees, and many more. So let's look at the golden rule again, where left subtree data must be lesser than equal to x and right subtree data must be greater than x. So if any node x is present, then all the nodes which are present in its left subtree must be smaller than the parent node, and all the elements present in the right subtree must be greater than the parent node x. Now let's take a look at the screen and see if you can spot the mistake in the invalid tree or not. So if you look closely, there is a violation. So if you see this binary tree, so all the data present in the left subtree of 5 are smaller than 5, and all the values present in the right subtree of 5 are greater than 5. Similarly, if you see for this node, all the elements present in the left subtree are smaller than 3. Similarly, if you see for this 8, the 8 left subtree has 6, which is smaller than that. So if you see this tree, if you consider this 2, the 6 is a right subtree of 2 and it is greater than that. But if you consider this root, you will see that the element present in the left subtree starting from 2, which has 6 as its right subtree, is greater than 5. So this is not a valid BST. So here the BST violation is happening. Because of this strict structure, searching a BST is fast and efficient. To find a target, you just compare it to the current node. For example, if we are looking for a node 6, right? And we started from our root node, which is at 5. Since 6 is lesser than 5, so we will discard the left subtree and we will start moving towards the right subtree. So here again, we will check whether the element to be searched, which is 6, is lesser than the left subtree element or not. Since 8 is greater than 6, so we will discard now the right subtree of 8 and we will move into the left subtree. And finally, when we will reach to this node, which is equal to this, we are able to get the key element in that node. So how many total number of nodes visited to find 6? 1, this 5, 1, this 8, and finally we found the element at 6. So total number of nodes visited to find 6 will be 3. So let's see this example with the code. So initially you will write a search method which will take input as root and target as element. So root will be 5 here and target will be 6 here. You will check if root is null or not. So if root is not null, we will simply return null. Since this is a recursive approach for searching a node in a binary search tree, so we have to have a base condition here. So this is our base condition. So if root is null, we will return from the function. Now we will check if the root.data is equal to the target or not. If it is equal to target, we will return saying that we have got the node which we are searching for. And then we will check if the target is lesser than root.data. We will search in the left subspace, that is in the left subtree. So we will call again recursively search function with root as root.left and target element as it is. And if the target is greater than root.data, we will search in the right subspace, that is in the right subtree. That is, we will recursively call search function with root.right, target. So let's see this example with this code as a dry run. So we will search 6 and our root is 5. So we will check if root is null or not, if 5 is null or not. So this condition will not work. We will see if 5.data, which is 5, is equal to 6 or not. So this condition will also not work. We will see whether target, which is 6, is lesser than 5 or not. So this condition will also not work. Finally, we will see since 6 is greater than 5, we will call search root.right, which is 8. So here it will call 8 with the target 6. So again, we will come inside our search function where now current root will be 8. We will check if 8 is null or not. So this condition will not work. We will check if root.data is equal to target or not. So this condition will not work. Now we will check whether 6 is lesser than root.data or not. So what is present in the root.data? 8. So this time it will say yes. It will call recursively search equal to root.left, because now we can discard the right search space. So now it will call search of root.left. And what is present in the root.left? 6, right? Now we will again come to the search function where the root will be 6 and the target will be 6. We will check if root is null or not. We will say no. Now this condition will work. Why? Because this time the root.data is 6 and target is also 6. So we will return from this function saying that we have found the element. So this is how you will search an element in a binary search tree. So what is the time complexity? So the time complexity will be O of n in case of worst situation. Why? So what if a tree is skewed, that all the elements are either present in the right subtree or all the elements are present in the left subtree. So in that case, our time complexity will be O of n, or else it will be height of the tree, which will be considered as a average time complexity. And what will be the space complexity? Since we are using recursion, so internally it will use the memory stack, which will be equal to the height of the binary search tree. So our space complexity will be O of h. Now what about adding data? So insertion is very simple. Here you have to use the search which we have already learned just now, and then we will add the node. So you will follow the exact same path which you have followed while searching for the value, and once you hit an empty spot, you will add your new node, right? So let's see this example. Suppose you have to add 5 into this tree, which is having 5 as the root and 8 as the right subchild of 5 and 6 as the left subchild of 8. And here you want to insert 7. So first you have to get the right spot for 7. And for that, we will use the same methodology which we have used in case of search. So the code is very simple. We will check if root is null or not. If the root is null, we will return new node of value so that we can add that node. Initially in the search case, we were returning null because our only goal was to come out from the recursion stack. So that was the base condition. And here we will tweak the base condition saying that if the root is null, that means we can add a new node with that value which we have to insert in our example. So we will return new node of value. And other than that, we will again check the same thing. We will check if the value is lesser than root.data or not. If it is lesser than root.data, we will recursively call the insert method with root as root.left and the value. And similarly, if the value is greater than equal to root.data, we will recursively call insert with new root as root.right and the value. So let's see this example with this code and a dry run. So we will call the insert method with root as 5 and the value as 7, right? We will check if 5 is null or not. So this condition will not work. So we will come to this condition. We will check here whether value, which is 7, is lesser than equal to root.data or not. Since 7 is not lesser than equal to 5, so this condition will not work. We will come to the else block, where we will recursively call the new root to its right, discarding the left subspace. So we will call insert root.right. And what is present in the root.right? 8. And what is present in the value? 7. So again, this insert function will be called. Now our root will be 8 and our value will be same, which is 7. We will again check if root is null or not. So this condition will again not work. We will come to this block. This time we will check if the value is lesser than equal to root.data or not. Since this time this condition will work, so now we will move towards the left subspace. And for moving towards the left subspace, we will recursively call root is equal to root.left. So we will call insert root.left, which is 6 and value as 7. So it will again call the insert method with root as 6 and value as 7. It will again check whether 6 is null or not. So this condition will again not work. Now it will check this condition where it will check whether 7 is lesser than equal to 6 or not. So this condition will again not work. Now it will finally come to the right subchild of root, where it will recursively call insert method with root is equal to root.right. And what is currently present in the root.right? Null, right? So it will insert null as the root and value as 7. So insert function will again get called with null, comma 7. So it will check that root is null. So it will return new node of value. So new node of value with 7 will get created and it will return here. So a new node will be created and it will return to the root.right. And what is present in the root.right? 6. So this 7 will get assigned to this 6. So what is the time complexity? So the time complexity is again same, which will be O of h, which will be the height of the tree. And since we are using recursive manner, so it will call our recursive stack, which will be of same size as of the height of the tree. So our time complexity will be O of h and space complexity will be O of h only. Now, what if you are seeking the extremes? That is the minimum and the maximum elements in a BST. So it's a very easy problem. For the smallest element, you just keep going towards the left side of the tree, and for getting the maximum element, you will move towards the right side of your tree. So to find the minimum element or smallest element, you just keep going towards the left. And for going towards the left, what will you do? You will assign a temporary variable to your root and you will keep iterating towards the left side until your left is a leaf node. So for that, you will run a while loop, which will check whether temp.left is not equal to null or not. And you will simply traverse towards the left side by keeping temp is equal to temp.left. And as soon as you hit the null, you will understand that this is a leaf node. You will break out from the while loop and you will return the temp.data, which will be 1 in our case. Similarly, for maximum element or largest element, we will keep going towards the right. So here also you will assign a temp variable for your root and you will keep moving towards the right side of your tree. And for moving the right side, you will do temp is equal to temp.right. And as soon as you reach the leaf node in your right side, you will break out from this while loop and you will return temp.data. So you must be wondering why we are learning how to find minimum and maximum element, because this will be an important thing to consider when we are learning about the deletion in our upcoming slides. So I forgot to mention that these two are LeetCode problem. The link I will mention in the description as well. Now we reach the boss level, which is how to delete a node in a binary search tree. Deleting is little tricky because no matter what we remove, we have to preserve the golden rule. That is, the elements present in the left subtree must be lesser than equal to x, and element present in the right subtree must be greater than x. So there are three distinct scenarios based on the node's children. So first case where you have to delete a leaf node which is having 0 children. Second case is where you have to delete a node with 1 child, when you have to delete this node. In that case, you have to change the reference of your child node to your grandparent node. And similarly, in case 3, when you have to delete a node which has 2 children, because in that case, you have to determine that which reference needs to get pointed. So let's look at case 1 and case 2 first. So for case 1, deleting a leaf node is simple. You just update the link of the parent to null. So suppose 3 is present in this node and you have to delete it. So you will just delete the parent reference of this leaf node as null. Similarly, case 2 is also simple, where you have to delete a node which is having 1 child. So suppose you have to delete 5, which is having 3 as 1 child. So you will simply remove the reference of 5 pointed by 10 to 3 directly. That is, you have to update the link of parent to the only child, whether it's on the left or the right. So now we will learn about case 3, where a node will have 2 children, which is where the real logic comes in. So for a node with 2 children, you need to replace the node with its in-order predecessor, which means the largest element in left subtree, or in-order successor, which means smallest element in right subtree. So as we have just now learned how to find the largest element in left subtree and smallest element in right subtree, so we will be able to crack this code as well. And the largest element in left subtree is known as in-order predecessor, and smallest element in right subtree will be known as in-order successor. So let's understand why we need to replace the node with its in-order predecessor or in-order successor only. So suppose you have to delete the node 10, right? So let's see the in-order predecessor. So what is the in-order predecessor of this? Means what is the largest element in left subtree? So this is the left subtree, right? What is the largest element? 7. And similarly, if you think in a different direction, what is the smallest element in right subtree? So this is the right subtree, and the smallest element is 12. So going forward, in just upcoming slide, we will learn that when we try to run the in-order traversal in case of binary search tree, it will give you the elements in sorted order. So if you have to remove this 10, so what is the next element which can become the parent? So it will be the in-order predecessor or the in-order successor. That is, it can be the largest element in the left subtree or the smallest element in the right subtree, right? Because when you write this in in-order manner, you will get 3, 5, 7, 10, 12, 15, and 18. So when 10 is gone, at that time, you will try to make 7 or 12 as its new root, right? Why? Because they are closer to 10. So 7 is nearest smaller and 12 will be nearest greater. That's why you will try to find the in-order predecessor or the in-order successor. So let's understand this code. We will call a method delete, which will take root and k. We will check, since it will be a recursive approach, we will write our base condition that if root is null, we will return null. Also, as we have seen, while inserting and searching, we try to search the node first, right? So for searching the node, we will check whether the element k is lesser than root.data or not. If it is lesser than root.data, then we can only found that node in the left side. So we will recursively call delete method by making root as root.left and assigning that value to root.left. Similarly, if k is greater than root.data, we will call recursively delete method again by making root is equal to root.right and assigning that value to its root.right. And finally, this is the condition where we will get that particular element. And here we are handling the case 1 and case 2. So the case 1 is that the node which we want to delete is a leaf node. That is, its left and right both child are null. So in that case, we will simply return null. Similarly, in case 2, we will check whether one of the left subchild or right subchild is null or not. So if one of the left or right subchild is null, that means the node is having one child only, right? And inside that, we will check whether we have to delete the left subchild or the right subchild. So if left subchild is null, we will return root.left. That means in that case, there will be no root.right. And similarly, if root.right is not null, that means our root.left is null. And in that case, we will return root.right. And finally, we will come to our case 3, where we can approach in either of any of the manner. Either we can get the in-order predecessor or we can get the in-order successor. So we will assign our root left subtree as temp variable, and we will keep moving towards the right, because in this case, we are doing in-order predecessor. That is largest element in left subtree. So we have assigned the left subtree as temp, and we will try to find the largest element. And for finding the largest element, what we will do? We will come towards the right side. So we will run a loop and check whether temp.right is null or not. And if it is not null, we will simply keep on moving towards the right side. And once we move towards the right side, and that is a leaf node, we will come out of this while loop and we will assign the root.data with the temp.data. And finally, since we started with in-order predecessor, that is by storing the left subtree, we will call the delete method again recursively towards the left subchild, where we will call delete of root.left, temp.data. So let's understand each cases with his code as a dry run. So let's see how to delete this leaf node. So suppose you have to delete 3. So your k will be 3 and your root will be 15, right? So we will check if 15 is equal to null or not. So this condition will not work. We will check whether 3 is lesser than 15 or not. It will say yes. So it will go towards the left side where it will recursively call delete with root.left. And what is present in the root.left? 12. So now delete will be called with 12. Now it will again check whether 12 is null or not. So this condition will not work. So it will check whether 3 is lesser than equal to 12 or not. So it will check the next condition where 3 is lesser than equal to 12. So it will again call root.left is equal to delete root.left. And what is present in the root.left? 3 only, right? So it will call delete method with 3, 3. Now it will check whether 3 is null or not. So this condition will not work. It will check whether 3 is lesser than equal to root.data or not. So what is present in the root.data? 3. So this condition will also not work. It will check whether 3 is greater than equal to root.data or not. Since 3 is not greater than equal to 3, so this condition will also not work. So we will come to this else block. Now we will check whether this node is a leaf node or not. So 3's left is null, 3's right is also null. That means it is a leaf node. So we will simply return null. So as soon as it returns null, the control will come to this delete where 12, 3 was called. So here it will assign 12's left as null. Similarly, for case 2, where you have to delete a node which is having one child, suppose you have to delete 5, right? So your root is 10 and your node to delete is 5. So it will check whether root is null or not. So this condition will not work. It will check whether k is lesser than root.data or not. It will say yes. So it will call delete of root.left. And what is present in the root.left? 5. And what is present in the k? 5 only, right? So again, this delete method will be called with 5, 5. It will check whether root is null or not. Since 5 is not equal to null, so this condition will not work. It will check whether 5 is lesser than equal to 5 or not. So this condition will also not work. It will check whether 5 is greater than equal to root.data or not. Since 5 is not greater than equal to 5, so this condition will also not work. Now it will finally come to this else block. Means we have found the element which we want to delete. Now we will check whether it is a leaf node or not, or it is a node with one child or not, or we will check whether it is a node with 2 children. So we will see whether 5 left is null or not. Since 5 left is not null, so this case 1 will not work. We will come to this else condition. We will check whether root.left is null or not. Since root.left is 3, so this condition will not work. But root.right is null. That means this condition will work. So it will come inside the case 2 block. Now it will check whether root.left is null or not. Since root.left is 3, we will return root.left value to delete function. So this delete of 10, 5 called delete of 5, 5, which returned the result as 3, right? So this 10 will be linked to this 3 now. Similarly, we will see for our case 3 as well. So suppose we are given this tree, so where our root is 10 and we have to delete 10 because it is having 2 children. We will check whether 10 is null or not. So this condition will not work. We will check whether 10 is lesser than root.data or not. Since 10 is not lesser than root.data, so this condition will also not work. We will check whether 10 is greater than equal to root.data or not. Since 10 is not greater than equal to root.data, so this condition will also not work. So we will finally come to this else block, which is because 10 is equal to 10. So here we will check the node which we want to delete is a leaf node, or it is a node with one child, or it is a node with 2 child. So we will check whether 10's left is null or not. Since 10's left is not null, so this case 1 will not work. Again, we will come to this case 2 where it will check 10 is the root and 10.left is not null and 10.right is also not null. So again, this whole condition will not work. Now it will come to the else block or case 3 where it will assign root.left to the temp. So what will be present in the temp now? 5. So now it will start the inorder predecessor code where it will try to find the largest element in the left subtree. And for finding the largest element in the left subtree, as we have seen earlier, we will move towards the right side of the tree. So we will check whether 5's right, which is 7, is null or not. Since 5's right is not null, we will assign temp is equal to temp.right. So now our temp will become 7. Now again we will check whether 7's right is null or not. Since 7's right is null, we will come out of this while loop and we will assign temp.data is equal to root.data. So now our root will become 7 and our root.left will call delete method recursively using root is equal to root.left, temp.data. So once you swap the values of 10 and 7, you will delete the old node which is 10 by either using case 1 or case 2, because right now 10 will be a leaf node. So it will be deleted using this case. So let's understand the time complexity. So the time complexity for these two, case 1 and case 2, will be O of 1. But if the node which we want to delete is having 2 children, in that case, the time complexity will be O of H, since we have to travel the complete tree to delete that node, since we are traversing for getting the inordered predecessor or the inordered successor. So our time complexity will be O of H, and since we are using recursion, which will internally use the stack, which will be of height H, so our space complexity will be O of H. So this is also a lead code problem. The link I mentioned in the description as well. Now let's understand how to construct a balanced binary search tree. So our goal is to build a tree from a perfectly sorted array. So suppose the array is given as 3, 5, 8, 10, 11, 12, 14, 20, 21, and 25. So your strategy will be of 3 steps. That is, you have to pick the mid element as the root, right? Next, you have to recurse on the left half, and similarly, you have to recurse on the right half. So what is the middle element? So suppose the middle element is 11. Since 0 plus 9 by 2 will give the middle element as 4, right? So 11 will be considered as a middle element, and what will be its left half? It will be from 3 to 10. And what will be in right half? It will be from 12 to 25. So the code is very simple. We are writing a method node build where we will keep the array, the left pointer and the right pointer. Since we will use the recursion approach, so we will write our base condition that if L is greater than equal to R, we will return. And since we have to find the mid element of the sorted array to consider it as a root, so we will do mid is equal to L plus R by 2. Also, we can use mid is equal to L plus R minus L by 2 to save ourselves from the overflow. And to build that particular node, we will do root is equal to new node of A of mid. Since every time the mid will give the root of its left and right subtree. And for building the left subtree, we will do root dot left is equal to build of A comma L to mid minus 1, so that we can build the left half of the subtree. Similarly, we will do for the right subtree as well, where we will write root dot right is equal to build of A comma mid plus 1 to R. And finally, we will return root. So let's see this example with this code as a dry run. Now, initially, your build method will be called with A comma 0 comma 9, right? So it will check whether 0 is greater than equal to 9 or not. So this condition will not work. We will do mid is equal to L plus R by 2. So our mid will be 4 now. So we will create a root node, which will be root is equal new node of A of mid. And what is present in A of mid? 11. So 11 will be created. And after that, we will call root dot left with build of A comma L comma mid minus 1. So we will call A comma 0 comma 3, right? Since mid was 4 here. Again, it will check whether 0 is greater than equal to 3 or not. So it will say no. So it will calculate the mid. So what will be our new mid? It will be 0 plus 3 by 2, which will be 1. So it will create a new node now with A of mid. And what is present in A of mid? 5. So 5 will get created. And in the next step, it will call root dot left as build of A comma L comma mid minus 1. Since mid is 1 now, so we will call A comma 0 comma 0. Since we will check that L is not greater than equal to R, we will again create a node with A of mid. And what is present in A of mid? 0. Since our L and R was 0, so our mid will be 0 now. So what is present in the A of 0? 3. So 3 will get created. Now again, we will call root dot left with build of A comma 0 comma mid minus 1. And what is mid now? 0. So it will call minus 1. Since L is greater than equal to R now, we will return. So we will assign this 3's left as null. As soon as the left side of 3 becomes null, we will come to the root dot right. So our current mid is 0. So we will call A of 1 comma 0. Again, it will see that L is greater than R. It will return null. So 3's right subchild will be null. So now we will return root. So as soon as we will return root, 3 will be assigned to the 5's left. Now when we are at node 5, our mid was 1. Now we will call A of build of A comma mid plus 1 comma R. And what was R there? 3. And what was mid there? 1. So our mid plus 1 will be 2. So we will call A of 2 comma 3. Again, we will try to find the mid there, which will be 2 plus 3 by 2, which will come 2 again. And what is present in the A of 2? 8. So a new node with 8 will get created. Now we will create the left and right subchild of 8. So for creating the left subchild, we will call build of A comma L comma mid minus 1. And what is L? 2. And what is mid minus 1? 1. Since when this build will get called, it will see that L is greater than R, it will return null. So 8's left subchild will be null. Similarly, for 8's right subchild, it will call build of A comma mid plus 1, which is 3, and R will be 3. So it will call build of A comma 3 comma 3. So it will see whether L is greater than equal to R or not. It will say no. It will again calculate the mid. So the mid will be 3 again. It will create a new node with A of mid, and what is present in A of mid is 10. So 10 will get created. And as soon as 10 will get created, it will call the root dot left and the root dot right. So it will call build of A comma 3 comma 2, where it will check again that L is greater than equal to R. So this will return null. So 10's left subchild will be null. Similarly, it will call build of A comma 4 comma 3. Again, it will see that L is greater than equal to R. So it will return null. So 10's right subchild will also be considered as null. And finally, it will return 10. And since 10 was the right subchild of 8, so 8's right will start holding 10 now. And when 8's left and right subchild is done, the control will come to 5. Since 5's left subchild and right subchild all are done, so the control will come to 11. Since 11's complete left subchild is done, it will call the right subchild of 11. So now it will call A of 5 comma 9. And now again, using the same procedure, we will create each node and we will link back to its respective parents left and right subchild. So what is the time complexity here? So the time complexity is O of n. So why the time complexity is O of n? Because every element in the array becomes a node exactly once. So for each recursive call, work done will be equal to O of 1. that is just create the node plus pointer assignment. Since O(n) element present in the array, so the time complexity will be O of n. And what will be the space complexity? So the space complexity will be equal to O of log n. Log n because of the height of the tree. Since we are using recursion and internally memory stack depth will be equal to the height of the tree, so the space complexity will be O of log n. This is also a LeetCode problem. The link I have mentioned in the description as well. Now coming to the final question of our day today. So how do you check if a binary tree is a valid BST or not? So just in previous slide, we have known that while deleting a node from a binary search tree, we either swap that node which is having two children with its inorder predecessor and its inorder successor. Whenever you do a inorder traversal for a binary tree, and if the output of the result is in sorted form, that means that binary tree is a binary search tree. So whenever you do an inorder traversal for a valid BST, it will always give you a strictly sorted sequence. So if you see this example, so initially don't consider this 4, right? It will not make it a binary search tree. So if you do a inorder traversal, what will you get? So you will see 2, then you will write 5, then you will come to 6, then 7, then 8, then 10, 15, 16, 18, 19, 20, and 30, right? So when you do a inorder traversal for this tree, you will get the result in a strictly sorted ascending order. So every time your current root.data must be greater than the previous data. So let's see the code for the same. So initially we will take a previous variable which we will keep as a infinite value. Now we will write a method is BST. Since this will also a recursive approach, so we will write our base condition, that is if root is null, we will return true. That means we have come to the leaf node. So this binary tree is a valid BST, and we will call recursively this function into its left and right subchild. And anytime we get a false, we will return false to its caller function. So we will check if is BST in its left subchild, which is root.left, is coming as false, we will return its parent as false only. Similarly, we will check if is BST of root.right is false, we will return false. And if your current root.data is lesser than previous, in that case also it should be false, because in that case we will come to the conclusion that this is not a valid subtree, since every time your previous data should be lesser than the current data. And if all these three conditions doesn't work, that means that is a valid BST. So we will return true. So let's see this example with a code dry run. So we will call is BST with root as 10. We will see whether 10 is null or not. Since 10 is not null, so this condition will not work. We will come to this condition. We will check if is BST of 10.left, which is 5, is false or not. Again, is BST will be called with 5. Since 5 is also not null, it will call its left subchild. So is BST will be called with 2. It will again check whether root is null or not. So this condition will not work. Now it will call its left subchild. This time, since 2 left subchild is null, it will return true. So control will come to 2. So what is the root.data here? 2. Since 2 is not lesser than equal to minus infinity or minus of math.max, so this condition will also not work. So we will store the root.data as previous. So our now current previous will be 2. Now we will check 2's right. Since 2's right is again null, so this condition will not work. So we will come back from this control of 2. So our control will come to 5. Since 5 left, which was 2, is already done, we will check whether root.data, which is 5, is lesser than the previous element or not, which is 2. So this condition will again not work. We will again save the previous as root.data. And what is present in the root.data? 5. So now our previous will become 5 from 2. Now we will call 5's right. And what is present in the 5's right? 8. So 8 will get called. We will check if 8 is equal to null or not. It will say no. So this condition will not work. Now it will see whether 8.left is false or not. Since 8.left is having 6 right now, so this condition will not work. So 6 will get called and this condition will not work. Again, 6 not having any left data, so it will return true. So it will return null. So control will come to 6. Now we will check whether root.data, which is 6, is lesser than equal to our previous or not. And what is present in the previous? 5. Since 6 is not lesser than equal to 5, so this condition will not work. Again, we will update our previous to root.data. And what is present in the root.data? 6. So our previous will get updated from 5 to 6. Now we will come to this condition. We will check that 6 right is having any data or not. Since 6 right is having 7, so is BST will be called with 7. Since 7 is not equal to null, so this condition will not work. We will check whether 7's left is null or not. Since 7's left is null, so this condition will not work. We will see whether root.data is lesser than previous or not. So what is present in the root.data? 7. And what is present in the previous? 6. So this condition will also not work. We will again store previous equal to root.data. So now this previous will get updated from 6 to 7. Now again we will call is BST with root.right. And what is present in the 7 side? Nothing. So it will return true. So this condition will not work. So we will come and return from the 7. Since 7 was called from the 6 right, so 6 rights is also done. So we will return from 6 as well. Since 6 was the left subchild of 8, so which means that 8's left subchild is done. We will check here whether root.data, which is 8, is lesser than equal to 7 or not. Since 8 is not lesser than equal to 7, so this condition will not work. again we will update previous equal to root.data. And what is present in the root.data? 8. So now our previous will get updated from 7 to 8. Similarly, we will keep checking and we will understand that the output which we are getting after doing the inorder traversal will be in always strictly sorted ascending sequence only. So what if there is a 4 present in the right subside of 6? So when you do inorder traversal, it will give the result as 2, 5, 4, 6, 7, which is not strictly in a sorted ascending ordered sequence. So in that case, when we will come to 6 and when we were calling 7, before that we will call the left subchild of 6, right? So that time our root left subchild will be called. So 4 will get called from 6, and that time when 4 will get called, 4 will call its left subchild. It will say true, so this condition will not work. It will come to this block. Now root.data will have 4 and our previous will have 5 till that time, right? Since 6 was updated after we came to the 6th node. Now we are at 4th node. Since 4 is lesser than equal to 5, we will return false. And as soon as we will return false from here, all the successive caller functions will return false as it is. And finally, we will say that this is not a valid subtree. And just like that, you have mastered BST. So let's do a quick recap. So our golden rule says that the left subtree is less than equal to the root and our right subtree must be greater than the root. Also, we learned about the core operations on binary search tree, that how to search a node, how to insert a node, and how to delete a node. And all of this runs in O of h time complexity. Also, for balanced trees, we understood what is a perfect balance, where we learned h is equal to log of n. And finally, your validation trick is to remember that an inorder traversal will always give you a strictly sorted array. So if you found this video helpful and helped you build that intuition, please hit that like button and subscribe to Techmine Guru. In our next lecture, we will dive into interview problems on binary trees. Till we meet again, keep learning, keep coding, and keep optimizing.